Good evening. My name is Aditya Kannan, and today I will be presenting my investigation of ramjets. This is part of Project 3 for the class AME 430 with Professor Justine Schlutz, and today's date is the 27th of March 2024. Here's a brief introduction to our investigation. Ramjets are a propulsion system utilized for high-speed supersonic applications. They're important because they provide a simple, efficient solution for atmospheric propulsion, where other options like conventional turbojets may fall short. The goal of our investigation is to understand the characteristics of the ramjet and its working principles using a MATLAB tool that simulates the pressure and Mach number through a ramjet nozzle or a converging-diverging nozzle. I compiled and compared various results from the tool with an analytical solution as well as empirical data in the form of normal shock function tables. This investigation is important because it firstly provides a hands-on understanding of the dynamics of a ramjet at various scenarios, and it also critically evaluates the accuracy of the tool. After our analysis, I found that the tool is indeed accurate with a relatively low margin of error for various values, and the graphical visualization it provides using MATLAB are as educational as they are accurate. The image on the left is of a Lockheed D-21, which is a ramjet-powered reconnaissance drone. The D-21 was mounted and launched from this SR-71 Blackbird and was used in various operations in the 70s until it was replaced by spy satellites. So, what is a ramjet? A ramjet is a propulsion system ideal for supersonic or hypersonic flight. It utilizes the forward speed of the aircraft to compress incoming air, eliminating the need for any rotating parts. The fuel is injected and mixed for combustion downstream of the inlet, where the resulting flame is stabilized by a flame holder ring. And the inlet cone that you can see on the left side of the diagram in the slide is intended to provide an efficient and stable shock structure throughout the Mach range. However, not all ramjets utilize an inlet cone. Here are some advantages and limitations of the ramjet. We start with some advantages. Ramjets have a simple design with few moving parts, none of which are rotating, making them lightweight and potentially inexpensive to manufacture and maintain. Ramjets are also extremely efficient at high speeds, between Mach 2 to 5, making them ideal for use in high-speed atmospheric systems. The set of simplicity in the design also allows for reasonably easy scalability in its uses. Now we talk about its limitations. Ramjets need to move at high speeds, usually well into their supersonic range, to compress air and operate efficiently. They cannot operate at zero airspeed, requiring them to be accompanied by another propulsion system or a launch vehicle. They are also not efficient at speeds under Mach 2, where they tend to consume fuel at a very high rate. The most important part of a ramjet is its converging-diverging nozzle. For our investigation, we will focus on understanding and modeling this component of the ramjet. A converging-diverging nozzle has three main components: the converging intake, the throat, and the diverging section. Functionally, it is similar to a Brayton cycle engine, such as a turbojet, where it at first compresses the working fluid, injects fuel, and then facilitates an expansion that accelerates the working fluid. Let's talk more specifically about how a ramjet works by discussing how the air travels through its various components. First, the air enters the engine through its inlet at supersonic speeds, where it is slowed down to subsonic speeds, increasing the pressure. After fuel is injected and ignited due to the high pressure and temperature in the combustion chamber, the pressure and the temperature of the air sharply increases. Now, we reach the converging-diverging nozzle. The air is compressed through the converging section until it reaches Mach 1 at the throat. Now, the diverging section allows the air to expand and reduces the pressure, accelerating it to supersonic speeds and creating a shock wave. The location of the shock wave in a ramjet can vary due to multiple factors, including the conditions at which it is operating in and the design of the ramjet itself. That said, a ramjet that is operating in ideal conditions will generate no shock wave, and this can be controlled by varying the back pressure of the engine. Now we talk about an important design variable of ramjets. So what is it? The area ratio is the ratio between the area of the exit and the throat of a ramjet nozzle. The throat area, also depicted by AT or A star, is the minimum cross-sectional area within the nozzle. The exit area, is depicted by AE, is on the other hand the maximum cross-sectional area of the ramjet nozzle. The diagram on the right provides a visual representation of the locations of the throat and exit areas. The area ratio dictates the dynamics of the air as it travels through the engine, making it a fundamental consideration when designing a ramjet. For this investigation, we must choose a realistic area ratio from an existing ramjet that we can base our models and calculations on. I decided to use the Wright XRJ-47 engine, which was developed for use in the Navajos 2 missile. The diagram on the left was obtained from the NACA Research Memorandum E55G22. The Wright XRJ-47 has a throat diameter of 38.8 inches and an exit diameter of 48 inches. Converting the diameters to areas and dividing them yields an area ratio of 1.53. We will model 9 unique flow conditions in this analysis. The diagram on the left depicts air pressure as it travels through a converging, diverging nozzle in various cases. Starting from case A, where the intake pressure is the same as the back pressure, we progress through each case by reducing the back pressure relative to the intake pressure until the shock leaves the nozzle itself. We will discuss the dynamics of the flow in detail in the following slides. Here's a moment to look through the summary of the various cases presented in this slide. For modeling the flow in the nozzle, we will be using a converging diverging nozzle simulator by William Davenport of Virginia Tech. To use this tool, we will provide it with two constants. First, our area ratio, which is 1.53, and the heat capacity ratio, which is 1.4 for air. We will be changing the pressure ratio to obtain the various flow cases outlined in the previous slide and obtaining values for Mach number and pressure throughout the nozzle. We start with case A. Here our pressure ratio is 1 and therefore there is no flow throughout the nozzle and the Mach at the throat is 0. Now we reduce the pressure ratio to 0.947 and 0.908 to obtain flow conditions similar to cases B and C, where the Mach at the throat is approximately 0.5 and 0.7 respectively. While the flow accelerates through the nozzle, it remains subsonic in its entirety. Now we decrease our pressure ratio further to 0.885, yielding a choked subsonic flow. The Mach at the throat reaches 1 from subsonic speeds, and the mass flow rate has reached its theoretical maximum. We can observe that there is a low pressure dip at the throat, after which it decelerates again to subsonic speeds. The pressure ratio is further reduced to 0.785, where a shock wave is generated in the diverging section of the nozzle. The flow is supersonic in the diverging section after the throat, where it reaches the shock and suddenly decelerates. Here, the pressure spikes higher dramatically, and the flow becomes subsonic for the rest of the diverging section. This is similar to cases E and F. At a pressure ratio of 0.609, the shock wave reaches its exit in our model. We can see that the supersonic flow is present in all sections of the nozzle after the throat, and subsonic flow occurs after the exit shock. We can see from the diagram that the pressure decreases through the nozzle as it accelerates and increases after the exit. At a pressure ratio of 0.4, the flow becomes overexpanded. An overexpanded flow in a ramjet leads to air expanding more than the ambient pressure, as we can see in the diagram, causing reduced thrust and potential flow instability as the air separates from the nozzle walls, reducing engine efficiency. The flow velocity and pressure profile through the nozzle is identical, but the pressure jump after the exit is less pronounced as the shock wave is obliquely positioned to the exit plane of the nozzle. Now, we reach the ideal state of the ramjet where there is no shock present throughout the system. The back pressure is equal to the ambient pressure and the flow is fully supersonic. The lack of a shock allows the ramjet to operate much more efficiently, but can be hard to precisely achieve in real-life conditions without careful design and control choices for the engine. Now, we perform an exercise where we modify the area ratio of the nozzle and observe its effects. We fix the pressure ratio at 0.154, similar to the no shock case, and the heat capacity remains 1.4. We consider two cases. In the first one, we increase the area ratio from our original 1.53 to 1.73, and in the second case, we decrease it to 1.43. It's clear that in the case where we increase the area ratio, the Mach number at the exit increases as well. That said, after further investigation, I found that a higher pressure ratio or lower back pressure is now required in order to achieve a no shock or design condition type flow. This could mean that while a ramjet with a more aggressive area ratio could travel faster, it would be more efficient at lower speeds, adding additional considerations to the design of the launch vehicle as well as other factors. Now, in our case with a decreased area ratio, our flow becomes underexpanded. The pressure at the exit is lower than the ambient pressure, causing a shock wave and flow disturbances and reducing the efficiency of the nozzle. A ramjet with a lower area ratio would theoretically be more efficient at lower speeds, on the other hand. Now, we go back to consider case E, where the shock is present in the diverging section of the nozzle. For this analysis, we record the area and pressure ratio before the shock wave using the tool and compare it with values using equations 9.51 and 9.52 from the textbook. These equations use a variable mx, which is the Mach number directly before the shock, and we can obtain this from the MATLAB tool. This is the initial condition for the total pressure ratio is 0.785, and the area ratio returns to the original 1.53 for this analysis. Equation 9.51 yields a pressure ratio before the shock of 0.254, while the tool yields 0.255. Equation 9.52 and the tool both yield an area ratio of 1.209. The discrepancy in the results is decidedly very low. Now, we will look at the flow rate flow after the shock, where we will obtain the Mach number using Mach number my using interpolation in table 9.3 and equation 9.55 from the textbook and compare it with the results. The initial conditions are the same as before. The equation and table both yield a theoretical Mach number of 0.685 and the tool yields 0.675. For the last part of our investigation, we will determine Py by Px, or the pressure ratio before and after the shock, using the equation 9.54 and compare it with values from the tool, which I obtained by selecting the points on the pressure graph before and after the shock and dividing the values. The tool and the equation yield similar values, around 2.65. Now we reach our conclusion. To summarize, ramjets are an effective solution for high-speed propulsion. However, as we demonstrated through the analysis, they are simple in their working and yet complicated. The high pressures and temperatures that are to be dealt with provide major engineering challenges, as well as the problem of delivering the engine to its operating speeds. The famous SR-71 Blackbird, pictured on the right, used a combination of a turbojet and a ramjet engine, giving it an operating speed range between 0 to Mach 3.2. Our analysis with the MATLAB tool yielded accurate results for each case, evidenced by the comparisons we performed of various values obtained from empirical evidence in the form of data tables as well as governing formulae. All in all, this presentation provided a hopefully useful insight into the working principles of the ramjet, the various conditions it operates at, and an analysis of the useful simulation tool by William Davenport. Here are the sources we used. Thank you very much.